You shall learn about some commonly used statistic in probability, relationship between mean of a sample and its variance and sample size. You will learn three fundamental theorems which are widely used in obtaining probability of occurrence of an event. These theorems are Chebyshev theorems, law of large numbers and central limit theorem. You also shall learn their significance through illustrations. To begin with, in earlier modules you have studied discrete and the continuous probability distributions. To recapitulate, Bernoulli's variable and its distribution, binomial distribution and Poisson distribution are discrete distributions where normal and exponential distributions are continuous distributions. You also know the characteristics of each of these distributions, that is their mean and variance. In this module, we will study the relationship between mean, variance and the sample size in a group of data. We will also study how mathematicians of 16 countries in Europe and Russia establish the importance of large numbers or bigger sample in the study of probability. First, we will discuss about some important statistics. We know that mean or the expectation measures the concentration of random variables and variance tells about the dispersion or the variability of random values around its mean. Further, measure of variability in original units is more convenient in applications rather than having in their square values. This led to the introduction of standard deviation in statistics, which is the positive square root of variance. Next, we will talk about relation between mean and standard deviation. A small standard deviation tells that there is a small deviation of sample random values from its mean value. When looking in the probability terms area under the curve of a continuous distribution with large value of a standard deviation will indicate a greater variability from its mean, and therefore the area under the curve will be spread out. However, a smaller value of standard deviation will have most of its area close to its mean. Same is true for discrete probability histogram. With this knowledge, can we answer problems like what is the probability that a variable x lies in a specified interval centered around its mean value, or how wide an interval is required around its mean so that 95% of the total values are included in the interval. To answer such questions is necessary to learn more about the relationship between mean and standard deviation of the probability distribution. Statement of the problem. In 19th century, a Russian mathematician P.L. Chebyshev showed that the fraction of the area between any two values symmetric around its mean is related to its standard deviation. Also, as area under the probability distribution curve or in a probability histogram adds to 1, therefore area between any 2 points will be the probability value between these 2 points. The probability that any random variable which lies within a given interval can be measured through the area that lies under its density curve or graph of fx within the specified interval. Chebyshev gave estimate of the probability that a random variable can assume a value within plus minus k standard deviations from its mean for any real number k. This remarkable theorem due to Chebyshev's is popularly known as Chebyshev's inequality theorem. This theorem is stated as if x a random variable with finite mean or expected value mu and finite standard deviation sigma, then the probability that x assumes a value outside the closed interval mu minus k sigma, mu plus k sigma is never more than 1 upon k square. That is, probability of x minus mu modulus is greater than k sigma is less than equal to 1 upon k square. In other words, the theorem asserts that the probability that a random variable x will deviate absolutely from its mean by k sigma will always be less than or equal to 1 upon k square. For example, probability for any value of a random variable to deviate from its mean by 2 sigma will at most be 1 upon 4, that is 0.25. In other words, no matter what the shape of distribution is, at most 25% of the values will fall outside plus minus 2 sigma from the mean of the distribution. An alternative way to express the Chebyshev inequality theorem is probability of x minus mu modulus is less than equal to k sigma is greater than equal to 1 upon k square. At least 1 minus 1 upon k square is the probability that any random variable x will lie within plus minus k sigma distance from its mean. Note that equation 1 and 2 are same statements. This is true for both normally distributed data as well as for data which is not normal or skewed. According to Chebyshev theorem, 75% of all the data points of a group of data falls within plus minus 2 sigma irrespective of the shape of the distribution. That is, if k is equal to 2, then 1 minus 1 upon k square is equal to 1 minus 1 upon 2 square is equal to 3 upon 4 is equal to 0.75. When data is normally distributed, we all know that 95% of the data points lie within the interval mu plus minus 2 sigma. Further, according to Chebyshev theorem, at least 89% of data points lie within 3 standard deviation of the mean, whereas for normal distribution, 99.7% of data points lie around its mean value. This difference is due to the fact that Chebyshev theorem is applicable to all types of data, whether it is skewed, multipolar or normal. Figure 1 given below explains application of Chebyshev theorem for 2 and 3 standard deviations when data is not normally distributed. Figure 2 explains for 2 and 3 standard deviations when data is normally distributed. When the Chebyshev theorem is relegated to situations where form of distribution do not matter or is unknown, therefore its results are usually weak. Further, when k is less than 1, then 1 upon k square is greater than 1 and 1 minus 1 upon k square is less than 1. For example, if k is equal to 0.5, then 1 upon k square is equal to 1 upon 0.025 is equal to 4 and 1 minus 1 upon k square is equal to 1 minus 1 upon 0.25 is equal to 1 minus 4 is equal to minus 3. When k is equal to 2, then 1 upon k square is equal to 1 upon 2 square is equal to 1 upon 4 is equal to 0.25 and 1 minus 1 upon k square is equal to 1 minus 1 upon 4 is equal to 1 minus 0.25 is equal to 0.75. Since we know that probability of occurrence of any event ranges from 0 to 1, therefore the Chebyshev inequality theorem is applicable only when k is greater than 1 and is trivial for values of k less than 1. Example 1. Average age of a professional employed by a software company is 28 years with standard deviation of 5 years. A histogram of age of the professionals employed with this company reveals that the data are not normally distributed as is rather skewed towards 20 and a few employed are towards 40. Apply Chebyshev theorem to determine within what range of age at least 85% of the professionals employed age would fall. Solution. According to Chebyshev theorem, at least 1 minus 1 upon k square proportion of the values are within the interval mu plus minus k sigma. Therefore, 1 minus 1 upon k square is equal to 0.85. Solving for k gives 1 upon k square is equal to 0.15 or k square is equal to 6.667 or k is equal to 2.58. Therefore, 85% of the values lie within plus minus 2.58 sigma of the mean. Given mu is equal to 28 and sigma is equal to 5, therefore 85% of the values will be within the age group of 28 plus minus 2.58 into 5 is equal to 28 plus minus 12.9 or between 15.1 and 40.9 years of age. Example 2. What is the smallest number of standard deviations from the mean that we must go in for if we want to ensure that we have at least 50% of the data of the distribution? Solution. Here we have to use Chebyshev inequality and work backward. We want 50% of the data of the distribution, which is 0.50 is equal to 1 upon 2 is equal to 1 minus 1 upon k square. Solving for k, we get 1 upon 2 is equal to 1 upon k square into 1 upon k square. By cross multiplying, we get 2 is equal to k square. Taking the square root of both sides, and since k is number of standard deviations, ignoring the negative solution to the equation, this shows that k is equal to the square root of 2, which is equal to 1.4. Therefore, at least 50% of the data will be within approximately 1.4 standard deviations from the mean. Before defining the law of large numbers, recall that if x, where I is equal to 1, 2, 3, 4, so on up to n, are random variables, then their sums s is equal to x1 plus x2 plus so on plus xn is also a random variable. It follows from this that if xi is identically distributed, then they must possess a common mean mu and a common variance sigma square. Then the expectations of S, that is ES, equals to the sum of expectations of all the individual random variables. That is ES is equal to EX1 plus EX2 plus so on EXN is equal to N into mu. Further, if X are random variables and are also independent, then additive property of expectation also hold good for the variance of S. This implies that Vs is the sum of the variance of individual xi, that is Vs is equal to Vx1 plus Vx2 plus so on plus Vxn is equal to n into sigma square. Next we talk about statement of the theorem. The first general formulation of law of large numbers was given by Jacques Bernoulli and was published posthumously in 1730. Bernoulli proved the law of large numbers, which is now one of the fundamental theorems in probability, statistics, and actuarial science. Bernoulli defined law of large numbers as if S represents the number of successes in n identical Bernoulli trials with probability of success P in each trial, then the relative frequency S upon n is very likely to be close to P when n is sufficiently large and fixed integer. That is, probability of S upon n minus P modulus is less than delta tends to 1 as n tends to infinity, or probability of S upon n minus P modulus greater than delta tends to 0 as n tends to infinity, where delta is greater than 0. Above are the different ways of expressing the theorem. The mathematical version of law of large numbers was first published by Chebyshev in 1929. This states that if xi, where I is equal to 1 to n, are independent and identically distributed random variables, and if exi is equal to mu, there exists then, when n becomes very large integer, the probability that random variable mean S upon n will differ from the common expectation mu of xi by more than any arbitrarily prescribed small difference epsilon is very close to 0. Mathematically, it is written as probability of x minus mu modulus is greater than epsilon tends to 0 as n tends to infinity, and alternatively
probability of x minus mu modulus less than epsilon tends to 1 as n tends to infinity. This simply tells that when n is very large integer, then the probability is very close to 1 for being close to mu or converges to mu. The larger the sample size, the closer the sample mean to the population mean. The Bernoulli's law of large numbers is also known as weak law of large numbers, as it does not say that when n tends to infinity means s upon n or the ex gets stabilized at mu or p. It leaves open that x minus mu modulus is greater than epsilon can happen a number of times, although at infrequent intervals. The strong law of large numbers states that when n tends to infinity, mean or s upon n or the ex converges surely to mu or p. That is, probability of x bar is equal to mu is equal to 1 as n tends to infinity. In other words, when n tends to infinity, sample mean will converge to the population mean mu with probability 1. Thus, law of large numbers are said to be strong because it guarantees stable long-term results of the averages of random events. This is certainly a strong mathematical statement. The illustration. Bernoulli may have thought that this concept of large numbers is self-evident, but it nevertheless is striking. For illustration, consider the game of golf. One cannot say with any certainty at all where one particular stroke of golf ball will end up. Still can say with very high accuracy that if 1000 balls are stroked, then how they will end up. Better yet, the more balls are stroked, the better the prediction will be. The law of large numbers is a powerful tool for taming randomness. The central limit theorem and the law of large numbers are two fundamental theorems of probability. The central limit theorem was introduced by de Moivre in the early 18th century. This theorem has been expressed by many forms. One important version treats it in terms of sum of identically distributed independent variables. According to this version, the central limit theorem states that distribution of the sum of averages of a large number of independent and identically distributed variables will be approximately normal regardless of the underlying distribution. The importance of this theorem lies in the fact that it virtually requires no conditions on the probability distributions of the individual random variables being summed. Thus, it furnishes a practical method of computing approximate probability values associated with the sum of arbitrary but independently distributed random variables. The central limit theorem is also stated in terms of relationships between the shape of population distribution, shape of the sampling distribution of means, and the size of the sample. The theorem says that if sample size is large enough and the sampling is done from a population with unknown distribution, either finite or infinite, then the shape of the sampling distribution of mean will be approximately normal with mean mu and standard deviation. Size of sample. Now question arises how large the sample size should be for a sampling distribution to be normal. The answer depends on two main factors. First, the degree of accuracy required for drawing inferences about the population under study. Second, size of the sample also depends upon the shape of the underlying population. If the population under study is very close to the normal distribution, then fewer sample points will be required. By and large, statisticians believe that the sample size of 30 is large enough if the population distribution is roughly bell-shaped. But if the population distribution is highly skewed or having multiple peaks, then the sample size would be much larger, and how much larger will again depend upon the accuracy required in the results. Significance of the problem. The significance of the central limit theorem is that It permits to use sample statistic to make inference about population parameters without having knowledge about the shape of the frequency distribution of that population. Its importance also stems from the fact that in many real applications, random variables of interest are sum of a large number of independent random variables, where central limit theorem justifies the use of the normal distribution. For instance, in finance, percentage changes in the prices of some assets or consumer durable goods are modeled by normal variables. Central limit theorem is also very useful in the calculation of probabilities in the sense that it simplifies the calculations to a very large extent by allowing to use normal probabilities.
We have learned about three very fundamental and widely applied theorems of probability, namely the Chebyshev theorem, law of large numbers, and the central limit theorem. The Chebyshev theorem establishes the relationship between mean and the standard deviation of a probability distribution. It holds true for both normally and non-normally distributed data. According to the Chebyshev theorem, 75% of the data points of a sample falls within plus minus 2 sigma of its mean irrespective of the shape of the distribution, and 89% of the data points lie within plus minus 3 sigma of the mean, whereas for normal distribution 95% of the data points lie with an interval mu plus minus 2 sigma and 99.7% of the data points lie within the interval mu plus minus 3 sigma. Since the probability of occurrence of an event lies between 0 and 1, therefore the Chebyshev's theorem is trivial for number of standard deviation k less than 1. The law of large numbers is a statistical concept that relates to probability. It is a law which is largely used by insurance companies to determine their premium rates and gamblers to find the probability of their winning the game to make profits. Thus, the law of large numbers is a powerful tool for taming randomness of the occurrence of an event. Statisticians are of the view that when the population is approximately bell-shaped, then a sample size of 30 is large enough to approximately normal distribution. But if the population is non-normal, having multiple peaks or is skewed, then the sample size should be much larger. Largely, it would depend upon the requirement of accuracy of the results. The central limit theorem gives an amazing result that when sample of large size is drawn from a population with unknown distribution, either finite or infinite, then the shape of the sampling distribution of mean will be approximately with mean mu and the standard deviation. That's all with this module. Thank you.